Saxon Advanced Mathematics, Lesson 66. This is a gem, you guys. I love this lesson. There's lots of fun things going on. Formulas for systems of equations. Okay, what the heck is that? Systems of equations we've been talking about for a long time, right? It's two equations that usually follow this pattern. ax plus by equals c, and dx plus ey equals f. And they go like this, and we're looking for a value for x and y that will make both of them come true, right? We've learned quite a few ways to do that. First, we learned to solve them by, I'm not going to write by every time, we learned substitution. That's where you plug in one into the other, right? That's where we started out. That's pretty easy. And then pretty soon after that, we learned by elimination. Okay, that's where you cancel out, you make them, you offset them, right? So they cancel each other out. And then you go on from there. That's pretty cool. Then we learned this, but we didn't spend much time doing it. We learned to solve it by graphing. And the idea there was that if you turned each of these into y equals mx plus b format, then you could graph each line, and the point where they intersected would be the solution to your system of equations. That's fun in theory, but it doesn't give you a very precise answer usually, right? Because it's out in the middle of your graph paper, and who knows what that fraction really is. So this is conceptually really nice, but we don't do it very much. Today we're going to learn a fourth way, and that is by formula. We're going to derive a formula that we can use to solve a system of equations. And very soon, we're going to learn the fifth one. I'm going to leave it a mystery by now. I really like the fifth one. It's fun. Okay, so what we're going to do is we're going to do example 66. We're not going to get into all of John's theoretical stuff. Okay, his instructions say this. Use abstract coefficients to find a formula for y, and then use the formula to solve for y in the system shown here. And then he gives us just a cute little system of equations. I'll repeat those instructions. I'm sure you're just sitting there going, what? I have no idea what she said. Don't worry. I don't know what I said either. Okay. So we want to solve for y. That means we're going to eliminate the x's, right? Because we want to solve for y. All right, what we're going to do is we're going to use what we call abstract coefficients to create a formula. So here's how we get the abstract coefficients. Okay, it's kind of like this system, only we're going to make it look way more fancy. It's going to be like this. The first term is going to be a1x plus b1x equals c1. And the second equation in our system is going to be a2x plus b2y, this should be a y, equals c2. Okay, so we gave them just the same letter, A, B, and C, but we called one equation the ones and one equation the twos. Now, we want to eliminate the x's, right? So that means we're going to multiply this one by, we'll do it the way John did. I'll tell you what I would do. This one we're going to multiply by A2. I would multiply this one by minus, let's just do it. I like to put the minus in the lower one. Okay. No, I've changed my mind. I want to do it this way so that I won't go crazy trying to make sure mine's the same as John's. All right. So we know we want the A's to cancel. So we multiply the top one by A2. We want this one to cancel. So the bottom guy's going to need A1. They're both positive right now. So somebody's going to need a minus, and we're going to give it to the top row. All right. So now let's multiply all of these through and come up with our new ready for elimination guy. So it's minus Okay? This looks really confusing. That's a 1. It looks messy. I like to keep the letters together first in numeric order, and then I prioritize alphabetic order over numeric order, right? So I put the A before the B, and I don't mind that it's a 2 before a 1. I keep the letters in order, okay? Now our second one will be positive A1, A2x plus A1, B2y equals, make sense? Now, we're ready to add them. And I guess I'll show you this in 2 steps. Let's write the positive one first. A1, B2y minus, right? They're very close. We have to be careful with that. The tedious thing about this is how close they all are to each other. Now what we want to do is we want to factor out the y's. Okay, I just factored it. And now we're going to divide away the crazy part. It's a small one. Sorry, I keep making those too big. Now what we have done is we have derived a formula that will allow us to calculate our y value. And rather than turn the page, I'm going to use my little notebook that I always keep on the side, and we'll do our final calculation in this little book. All right. Now, this was our original equation. Let's make sure we name them. This is A1, B1, C1, and this is A2, B2, C2. Okay, our formula, I will write over, it says y equals, and then it's this whole chunk, right? Okay, so what we have done is we have used these abstract coefficients to derive a formula for y. Told us we were supposed to be solving for y, so that meant we knew to eliminate the x's. We just multiplied by the coefficients in front of the x's and threw a minus sign on 1. We did some hot and heavy algebra here to get through just the basic abstract equation work that we know how to do. This is the formula we came up with. Now we're ready to plug in these values so that we can simplify and solve this crazy monster, right? So what I'm going to do is create a whole lot of buckets. Watch that minus sign. These are all being multiplied, obviously. Now we'll use our values here. I guess I'll go like this, so you can kind of see. All right, A2 is 4, C1 is 8, A1 is 3, C2 is 3, A1 is 3, B2 is 5, minus A2, 4, and B1, 2. I'm going to double check that and make sure that I did not do anything crazy. I've got a minus sign wrong somewhere. Oh, here it is. This should have a minus right there. Right? I dropped that minus sign. I multiplied the two letters together, but I dropped that minus sign. So that means the A2C1, this should have a minus sign. A2C1, this should have a minus sign. And then up here, this should have a minus sign. Okay. So, let this be a lesson to you kids. When you're distributing when you're doing your multiplications, don't drop your signs. Okay, so let me double check now and make sure I'm right. Yes. Yes, okay, otherwise it's correct. So now we're just ready to do the multiplication. 4 times 8 is 32 minus plus 9 over 15 minus 8. And this equals minus 23 over 7. And that's the right answer. Yay! Okay, so what we just did was we solved our system of equations by using a formula based on the abstract coefficients, okay? And my mistake, again, was when I was distributing this across all three parts, I forgot to distribute the minus sign. And the way I caught that, you guys, was that when I filled in all of my values, I stopped before I did my calculation. I was almost done, but I stopped and checked that much in the solution to make sure I'd put everything in the right place. And what I found was, yeah, the numbers were all in the right place, but I was missing a minus sign. So then I looked back through my work to find out where I might have dropped it, and I found it up here, okay? Remember that making mistakes does not mean you're dumb. Making mistakes is the best way to learn. And my mistakes, almost always, 99.9% of the time, you guys know this, they usually come from something really, like, I don't want to say dumb, but something really trivial. I copy the problem wrong. Or I do something like this where I just drop a sign, or I do a crazy multiplication. I don't do that too much, but I'll probably do it on the next problem. Little mistakes. And what that just reminds me is constant attention, constant focus. I can't let my mind drift at all, or I will lose something important. You may have a different little bugaboo that is your thing, but we all need to learn where our mistakes tend to come from, and then we can correct them and plan for them, okay? Yay. One of the things I've noticed is that when I'm teaching, if I talk through what I'm doing, I tend to do it more accurately. If I stop my mouth and I'm just zooming things around, that's when the little mistakes crop in. A lot of students I know have the same sort of preference, and they often talk out loud to themselves as they do their work. It's really interesting how some students really rely on that. So if you're one of them, hey, be proud. There's no shame in that whatsoever. Whatever it takes for you to get the right answers is what you need to do. Okay, that's all for this problem. But again, we have learned our fourth. We already knew these three. We've learned this one, and I think this one's coming up really soon. So that'll be exciting, all right? This one, honestly, it makes me feel, happy that I know how to do it, but it's kind of a pain, right? It's a lot of fooling around with a bunch of little subscripted numbers. All right, what we are going to do is learn some more about our sinusoids, friends. We're going to learn about phase shifts. Phase shifts. Grace, we're not going out there right now. She smells the cookies. And period changes. This overlaps a little bit about what we've already talked about. But I'm just going to kind of rewind. So if I'm telling you things you already know, a second, I have to let this dog out. She's aping. If I'm telling you things you already know, I'm just crossing over. Hang on just a second, you guys. Oh, they're ahead of you. Come on, Grace. Sorry, I abandoned you, students. My daughters were baking in the kitchen and they left, and Gracie wanted to go in there, of course, because it smells like heaven. So I just wanted to make sure that everything was put away. All right, we want to talk about our sinusoids and what's going on with them. And what I want to show you is the basic form of the equation that we've been working on. And I think I'm going to have to go get that dog. Grace! Hang on. Sorry. Entertain yourselves. Okay, that's enough. Good girl. Come on. Okay, we're back. All right. And this very same format is used for cosine as well. Okay. We always want to use what's called the factored form of the argument. We could see it like this, c times theta minus, those two could be multiplied. We always want to factor it here. I don't remember that ever being a problem, but just something to point out. A, as you well know, is the center line, right? B is the amplitude. Those things we don't really have to do too much work to figure out. We just glance at the chart and figure it out from there. C is the period. A second, I'm looking at. C is the period, yes, which is equal to 360 divided by the period, or sometimes we'll do these in radians, so then it would be 2 pi over the period, okay? Again, when we get that unit circle going with you guys, working in radians is going to become a lot more natural and a lot more easy. And then this guy is, it's the period coefficient, I should say. And we calculate it as that or that. And then this is the phase shift. And it helps us move the curve up and down. Now, the fun thing, and this is for both of these, by the way. I'm not just pointing to the cosine. It's the same. The fun thing, oh, and remember that the phase shift, it is, if it's negative, that means it goes that way. And if it's positive, then it goes that way. It's kind of confusing. I'll show you when we get to the pictures. All right. And we just have one example here. It's example 62. No, it's not. It's example 66.2. Write both the sine and cosine equations of this sinusoid. Okay, let's look at it. And I think I'm going to draw it. Well, I don't know if I should. That would take a lot of time. Let's not. Okay, Here's the interesting thing. A sine can be both a cosine and a sine curve at the same time. We just consider it to be phase shifted one way or the other depending on which function we're looking at. Did that make any sense? I don't know. Let's talk about this one. Let's start by setting up the A, B, C, and then D. For sine and cosine, the center line, amplitude, and period coefficient will always be the same. D, the phase shift, is the only thing that's different for sine and cosine. So that's cool. That means 3 of the values you only have to figure out once, and it's just the 1 that you have to do twice. All right, let's look at our guy. What is our center line? Well, sometimes you have to look at the amplitude to figure it out. Let's see. This goes up to 7 and down to -1. That is a range of 8 points, right? Because it's 7 back to 0, and then 1 more down is 8 points. So that means our amplitude is 4, right? And the center line must be 3. The amplitude is 4, and the center line must be 3. I figure that because if it's 8, here's my picture. 8 is the total difference. I divide it in half, that's 4. That means I go 4 up and 4 down. So what number is 4 less than 7? 3. And then I double check it. 3 minus 4 gives me the -1. So that sounds right. So now I've got, and John shows it here, he's filled in his A and B, his center line and his amplitude for both of his sinusoids, the sine and the cosine. The sine is on the left, cosine's on the right. What I'm doing, I'm approaching it slightly differently. I'm just making a list of the 4 variables. I'll get them all figured out, and then I'll write both of the equations in that format. Whatever you want to do. All right, because I don't want to erase, right? He's just putting in the letters and filling them in. Okay, now we want to do the period. So what we need to do is we need to pick one point on the curve where we can measure it the same. Okay, so sometimes you might want to measure the top from top to top or from bottom to bottom. I like coming up and coming up because usually we can see really neatly where it crosses. That's easier to me than trying to read across the gap. So I like where it's crossing the number line. So from -225 to 315 is one period, one full rotation of the curve. And by the way, it doesn't matter where I measure it from. As long as I'm consistent, I could measure top to top or bottom to bottom. It doesn't matter whether it's sine or cosine. I'm measuring it from the beginning of a sine curve to the beginning of a sine curve, but it's the same for a cosine. So it's just whatever's easier for me. So what I need to do to find out the period is I need to add 315 to 225, right? Because that's the whole gap. So the period equals, it's going to be 360 over, what were the numbers I said? 315 and 225. And that equals 360 over 540. Okay, so I can see that my coefficient is going to be a fraction, which makes sense because the periods are bigger than 360, right? So now I have to try and reduce that. Okay, I can divide by 10. 9 goes into both of these. 9 goes into 36 4 times. 9 goes into 54 6 times. Oh, okay, I can take that down to 2/3. So that means that my coefficient is 2/3. And this is how I calculated it, right? There's my whole big calculation, right? Again, the period coefficient is the same whether it's sine or cosine. Now, to find the phase shift, I need to find how far I have to go away from 0 in order to get the starting place for my curve. Now, here's the interesting thing. we usually look for, so sine starts where it's coming up across the line, right? Not going down across the line, but coming up. It's coming up here and it's coming up here. So we could write the phase shift as a negative 225 shift, or we could write it as a positive 315 shift. What we usually do is choose the one that is closest to 0. So that means I would choose this one. So my shift is negative 225, so that means I need to write it as plus 225, right? Because it's when I go this way from 0, it means it's plus, right? Because it's the opposite sign. And this is for sine. And now we'll figure out the phase shift for cosine. Cosine begins, the cosine function begins when the period is maxed out and we start to go back down. So it's at the height. So again, we could do it at this negative 90, or we could do it at 450. We choose the value that's closest to 0. So we see that it's a negative 90 shift, and that means we're going to write it in our equation as a plus 90. Okay, so now we're ready to write our equations. We're using this format. So for the sine curve, we'll say y equals 3 plus 4 times the sine of 2/3 theta plus 225. And I double check this one more time because it'll make you crazy. It's supposed to be negative, so I changed it to positive. That means I'm shifting 225 that away. Yes, that's right. And now I do the very same thing for my cosine. Same center line, same amplitude, different function, same period size, but my phase shift is different. All right? Those are correct. Let me double check. Yes. Plus 225 plus 90. Beautiful. So I love these because I love the idea that a particular curve, and in this case, this one, it can be a sine curve or it can be a cosine curve, and we can write it as either way. I love that. Something in that just really appeals to me, that the numbers are, the patterns are similar, and yet different. I don't know what to say about that. I'm just overwhelmed by the beauty of the whole enterprise. All right, I hope this makes sense to you. We'll talk about it. I think after you try a few problems, it'll fall right into place. That is the end, my friends, of lesson 66. We had fun, didn't we? We talked about the systems of equations, and then we talked about the shifts. Yay, I love this class. Okay, thank you. Goodbye.